Ladies and gentlemen, a very good afternoon and welcome to the Institute of Advanced Studies Lee Kong Chian Distinguished Professor Public Lecture. I'm Arpit, the Vice President of Graduate Students Club for NTU School of Physical and Mathematical Sciences. It is my esteemed honor to be the MC for today's public lecture. The lecture is organized by the Institute of Advanced Studies at Nanyang Technological University with support from the Lee Foundation and the National Research Foundation in Singapore. In the view of the latest COVID guidelines, the event has been made possible in a hybrid mode. We are happy to welcome our audience here at the Nanyang Auditorium, and we also welcome those joining us on the live stream. To begin with, may I now invite on stage Professor Simon Redfern, Dean, College of Science, to deliver his welcome address. Professor Redfern, please.
Distinguished guests, ladies and gentlemen, I'm delighted to welcome you to this lecture today, in particular because this is, I believe, the first in-person lecture of the Institute of Advanced Studies since this time 2 years ago. And so we're enjoying today our distinguished lecture from Stuart Parkin on spintronics. Stuart is a physicist with a background that I was interested mimics mine in a very small way, in as much as we have both lived in similar places. So Stuart was born in Watford, educated in Manchester, and then moved to Cambridge, where he carried out his undergraduate and postgraduate training before joining IBM in Stanford, and he's a visiting professor at Stanford University and became a research fellow at IBM. Stuart is noted for a number of remarkable achievements. He won the Millennium Prize in 2014 for his understanding of giant magnetoresistance and its use in memory devices, in particular in read heads for magnetic drives. This transformed the density of digital information that could be stored and read in such devices. He's since worked in spintronics, which we'll hear about today, and has collected along the way a string of notable commendations and prizes. He's a Fellow of the Royal Society, he's a member of the National Academy of Sciences. I could go on at length, but I shan't because I really want to hear from Stuart today. But before we do, I would like to invite the President, Subra Suresh, to join us to say something about the science that Stuart will be talking about. So thank you.
Thank you, Professor Redfern. Now I would like to invite our guest of honor, Professor Subra Suresh, NTU President, for an opening address.
Good afternoon, everyone. Professor Stuart Parkin, distinguished guests, colleagues, students, those joining us online, a very good afternoon. It is my pleasure on behalf of NTU to welcome Stuart to give this IAS Lee Kong Chian Distinguished Professor Public Lecture at NTU. I was just talking to Stuart a few minutes ago. We met each other in the US, I think, for another lecture. I forget where it was, whether I gave the lecture or he gave the lecture, but we met at an event or at a conference about 10 years ago. I would like to convey my gratitude to him for joining us today in person to deliver this lecture. He's currently director of the Max Planck Institute of Microstructure Physics, as well as the Alexander von Humboldt Professor at Martin Luther University of Halle-Wittenberg in Germany. He's the inventor of racetrack memory, and an IBM Fellow. He is renowned for his work in spintronics, as Simon just mentioned, which brought about breakthrough data storage technologies. Especially our generation, and by our generation, I'm including a couple of generations here, would be familiar with hard disk drives and memory chips used as storage space for very large pieces of data or amount of data. But 2 decades ago, Professor Parkin had already started thinking about the limitations of this basic technology and wondered if there was a better way of designing a disk drive without moving parts. This led him to come up with the concept of spintronics-based memory or racetrack memory, which has the potential to access data significantly faster than hard disk drives at the same low cost. In fact, with Professor Parkin's racetrack memory device, it is estimated that the performance could be many orders of magnitude better than the current disk drives we know today. To visualize how racetrack memory works, in fact, he will explain it a lot better than I can possibly do, I understand that IBM has a way of describing it in a very creative and understandable manner. Imagine a city of skyscrapers of magnetic material, each one only hundreds of atoms wide, with each floor in the skyscraper containing a single bit of data. The data shoot up and down the skyscrapers through a supersonic elevator via the chiral spin orbit torques that Professor Parkin will be explaining to us shortly. By passing spin-polarized currents through the data, the magnetic data can be moved up and down the skyscrapers, which are vertical racetracks, enabling massive quantities of data to be stored. The study of spintronics, or spin electronics, can help in solving major problems that currently exist in today's conventional electronic devices. The transition from conventional electronics to spintronics technology can be seen as a seismic shift, as it opens immense possibilities in the development of intelligent technology using non-volatile memory devices. With the recent discovery of complex chiral spin textures and the ability to atomically engineer and manipulate magnetic heterostructures, I'm sure that Professor Parkin's talk will provide you with a much better understanding of the exciting possibilities in the novel storage technologies for spintronic memories. To the students and young scientists who are joining us today, both here in the auditorium and online, I hope that today's lecture will help you connect the importance of basic research and science to large practical applications of major societal significance on a global scale that involve technology and humanity that accesses that technology on a continuous basis. In closing, I would also like to thank the Lee Foundation and the National Research Foundation, Singapore, for their support of this lecture, and to the Institute of Advanced Studies and the NTU Events Office for organizing this event. I wish everyone a very enjoyable afternoon and evening. Thank you.
Thank you, Professor Suresh. Now, let's start with Lee Kong Chian Distinguished Professor Public Lecture. Our eminent speaker for today is Professor Stuart Parkin, who is well known for his work in spintronics that resulted in new data storage technologies. Professor Parkin is the director of the Max Planck Institute for Microstructure Physics and Alexander von Humboldt Professor at Martin Luther University. Professor Parkin's discovery in spintronics have enabled a more than 10,000-fold increase in the storage of magnetic disk drives. For his work that enabled the big data world of today, Professor Parkin was awarded the Millennium Technology Award from the Technology Academy Finland in 2014. Most recently, he received the King Faisal Prize 2021 for his research into 3 distinct classes of spintronic memories. Professor Parkin has received numerous honors from around the world, which include being the Fellow or member of the Royal Society of London, Royal Academy of Engineering, National Academy of Sciences, National Academy of Engineering, German National Academy of Sciences Leopoldina, Royal Society of Edinburgh, Indian Academy of Sciences, and TWAS Academy of Sciences for Developing Countries. Before we invite Professor Parkin on stage, please note that the question and answer session will take place after the talk via Slido. Please scan the QR code before we begin the lecture and key in your questions as the lecture progresses. Now let's welcome Professor Parkin on stage with a big round of applause. The title of his talk is Chiral Spin Textures and Chiral Spin Orbit Talks for Spintronic Memories. Professor Parkin, please.
Well, thank you very much. I'm very honored to give this distinguished lecture today, and I want to thank the President for giving such a wonderful introduction. I hardly need to give my talk at all. But what I'd like to do is tell you a little bit about spintronics and how spintronics has enabled 3 important classes of memory devices. And I'd like to, in particular, tell you something about recent work on very interesting chiral spin textures, which are highly useful for a wide variety of applications. And as the President mentioned, I moved to Germany 5 years ago from IBM Research, which is based in San Jose in California, where I was for 30 years. And Max Planck is a wonderful place to do research because it really wants to explore fundamental research, but nevertheless research that can have an impact. And I think spintronics falls into this type of research. On the first foil, you can actually see a drone view of the laboratories on the left that I built in the last 5 years. And in particular, we built a fantastic set of capabilities for building atomically engineered structures that I think are very important to develop materials and devices that can impact spintronic technologies and beyond. So if I move to the next foil, then this shows you what the Max Planck Institute in Halle looks like in the winter. You're very fortunate in Singapore to have, it's very warm. In Germany, we have quite a lot of snow. And this is a picture from actually last year. This institute, since I joined 5 years ago, I've completely rebuilt almost from the ground up. And now we have 2 other new directors, including myself, both focusing on materials and devices that could impact a wide variety of technologies. And also in the last 5 years, I've hired a lot of very wonderful young people to do their PhDs with me in Germany, as well as postdoctoral scientists from all over the world, including from Singapore. So maybe I just preface my lecture by reminding you that a very important technological breakthrough took place 550 years ago. It turns out this was actually in Germany, in the city of Mainz. And the Johannes Gutenberg invented a technology for printing books, the movable type press. So before his invention of this technology, then information was stored by writing on pieces of paper. But with the invention of the printing press and the ability to print books, one could spread knowledge more widely. And this led, in some sense, to the age of the Enlightenment in which we still live. Well, this technology of books, paper, it's an analog technology, and it's lasted more than 550 years. But this changed, perhaps starting 50 years ago, when IBM in California, in San Jose, invented the magnetic disk drive. And this is shown in the middle of this picture. A magnetic disk drive is a series of glass platters which are rotated mechanically, and on one side or both sides of the glass platter is deposited a thin magnetic layer. And this magnetic layer is magnetized in directions. Either it's magnetized up or it's magnetized in the opposite direction. And information is encoded in boundaries, interfaces between these regions magnetized in one direction and in the opposite direction. And so this is the concept of digital data storage, in which data is stored either as a 0 or as a 1, the presence or absence of transitions between magnetic regions pointing in opposite directions. And in this foil, you can see on the bottom left, you can see an image of some of these magnetic bits using a modern technique of magnetic force microscopy to image them. Today, these magnetic regions that store a single bit would be of the order of 20 nanometers in width, so they're very tiny. So why is this important? It turns out in 50 years, the capacity of a magnetic disk drive was increased by about a billion times. And this has led to the possibility that all digital data can be stored in magnetic disk drives. And about 70% of all digital data today is stored in these magnetic disk drives. And if you look in the clouds, so to speak, you would see massive numbers of magnetic disk drives, these mechanical drives, storing vast quantities of digital data. And essentially, we moved to the digital world just a decade ago. And this has meant big changes in our lives and in the lives of companies, and in fact, in the development of entirely new companies whose business model is based on exploiting the digital data that is stored in these magnetic disk drives, companies like Facebook and Google that you're very familiar with. So if we look at how the evolution in the storage capacity of the world has evolved over the last 30 years, this is a paper published in Science 10 years ago. And basically, these authors explored what types of devices were analog, what types of devices are digital, and how much data these respectively stored. And you can see that approximately in the early 2000s, we moved from an analog world, the orange devices, paper, videotape, books, to the digital world. And in the last 10 years, we've moved to a digital world in which, as I said, 70% of all digital data is now stored in magnetic disk drives. So this has been an amazing technological revolution in which we moved into the digital era of data. And I want to just briefly remind you that at least for magnetic disk drives, as was mentioned in the introduction, the last 10,000 times improvement in a disk drive was due to a spintronic device that I invented 30 years ago. Now, spintronics, what does that mean? That means today, nearly all electronic devices in the computer, the computing elements and the storage elements are based on the electron's charge. So in a transistor, we turn on and off an electric current composed of electrons by a voltage. We gate these transistors. That's a switch. And on the other hand, we store information, for example, in a dynamic random access memory in a capacitor where we basically store information as a number of electronic charges. But the electron has another property, a quantum mechanical property of spin that was discovered 100 years ago. And the spin of the electron, you can imagine it's like a spin angular momentum that can rotate in one direction or the other direction. Quantum mechanically, this means that the spin can only take two values. It can be spin up or it can be spin down. And by creating currents of electrons whose spins are oriented in one direction or oriented in the opposite direction, we can create new devices with new phenomena not possible by simply using the electron's charge. And this is the concept of spintronics. We use the electron spin, we create currents of electrons with their spins polarized in one direction, we manipulate these currents, and then we detect these currents in order to build new types of devices. That's the basic concept. And so let me just remind you, tell you then that in a magnetic disk drive today, the device that reads the information, and as I said, it's a rotating disk. On the surface of the disk is a so-called recording head. This recording head floats above the surface of this magnetic film, 1 nanometer above the surface when it's reading or writing, and it reads the fringing dipole fields between the boundaries, between regions magnetized in opposite directions. So in this cartoon, you can see these blue and red regions correspond to magnetic bits 20 nanometers in size, magnetized either up or down, but the information is encoded in the presence or absence of these transitions from one magnetic region to the other. And these transitions give rise to dipole fields. In the same way, let's say a refrigerator magnet, a north pole and a south pole, there will be fields emanating from the north pole, magnetostatic fields. And these are detected by the head that is moved over the surface to detect these transitions, to detect the digital information. And today, that head is a spintronic device, which I invented 30 years ago. And this shows how an evolution of that device that is now used today in that magnetic disk drive to read information. And it consists, as you can see in this cartoon, of a sandwich of two magnetic layers separated by, and these are shown as red and blue, representing the direction of the magnetization of these magnetic layers. They're separated from one another by an ultra-thin insulating layer, shown in gray, which is about 1 nanometer thick. When current is passed from one magnetic layer to the other through this insulator, the electron current that's extracted from the surface of a ferromagnetic material will be spin polarized. There's a preference for electrons of one spin orientation to be extracted when you take current from the surface of a ferromagnet through an insulator or through vacuum. And when the second magnetic layer has its magnetization pointing in the same direction as the first one, these spin-polarized electrons can find empty states of the same spin orientation, and so the current can flow easily. That's shown in the upper cartoon for the two red layers whose magnetizations are parallel to one another. But when we switch the direction of magnetization of one layer from the red to the blue direction, then there's a reduced number of available states of the same spin polarization, so the electronic current is reduced. And this difference in current is what is called a tunneling magnetoresistance. And at room temperature, these devices show changes in resistance of several 100%. So these are very large changes in resistance that can be easily detected by passing a current through the device or by proper spin engineering, using some concepts that I invented, we can manipulate these devices so they respond to very, very tiny magnetic fields. And then as the device is rotated and floated above this magnetic media, the magnetic moment of one of those layers will wobble in the presence of these dipole fields and cause changes in the resistance that can readily be detected. And using such a tunneling magnetoresistance spin-engineered device, we can detect magnetic regions which are 10,000 times smaller than was previously possible, making the possibility to increase the storage capacity of these magnetic disk drives about 10,000 times. So this is the essence of a spin valve or magnetic tunneling junction recording read head that is used and has been used since 2007 in all magnetic disk drives. Now, at the same time, it's possible to use a similar device where we engineer the magnetic layers slightly differently as a memory element. We store information now digitally as a direction of the magnetic moment of one of these layers, pointing either in the red direction or in the blue direction. And this is a non-volatile memory element because the information is encoded as the direction of the magnetic moment until we change that direction. And we can read the information extremely easily and quickly because we only need to pass a tiny current through the device to detect whether it has a high resistance or a low resistance, whether it's a 1 or a 0. And we do that by putting this device within a cross-point array, an array of metallic wires. The device sits between these wires, and this is a standard configuration for many memory technologies today. Using this magnetic tunnel junction as a magnetic storage element, we can build a very powerful memory that can be read and written very rapidly, is non-volatile, and that consumes very little power. And moreover, these devices can be scaled to smaller dimensions than is possible with many of the existing charge-based technologies of today. And this is why this technology is very interesting. And at the same time, I just wanted to point out that it's taken quite a bit of time to go from conception, we did that in 1995. At that time, the magnetic tunneling junction devices that existed had resistance values 100 million times too high to be technologically relevant. And the tunneling magnetoresistance was 10 times too small to be technologically useful. Nevertheless, within a small number of years, in 1999, I demonstrated that we could make magnetic tunneling junctions which had resistance values 100 million times smaller than had been demonstrated, and with sufficiently high tunneling magnetoresistance that a few years later we could build a 16 megabit demonstrator with a completely with electronic circuits for reading and writing these tunnel junction devices. Nevertheless, it's still taken another decade or so before Samsung announced just 2 years ago that you could now buy from Samsung this magnetic memory technology as basically a replacement for the embedded dynamic random access memory. So now this is a technology that is widely used in the industry. But I wanted to point out it's taken more than 20 years. On the other hand, the introduction of the read head based on originally a metallic sandwich rather than two magnetic layers separated by an insulator, two magnetic layers separated by metal, copper, we could use that in a magnetic disk drive. And this only took, it seems like a short time, 6 years from my invention to IBM introducing it into magnetic disk drives. And within 3 years, all magnetic disk drives used this technology because in that 3-year period, the storage capacity of these magnetic disk drives was increased by more than an order of magnitude. It made such a huge difference almost immediately. I must also like to point out, though, that in the last few years, the ability to increase the storage capacity of a magnetic disk drive has been more limited. Essentially, one has reached the end of this roadmap of the technology. It's no longer possible to continue to shrink these magnetic regions because they become thermally unstable. And so we need to find an alternative if we want to increase further our ability to store the ever-increasing amount of digital data that is produced today. And that means we need a new technology, and this is a technology, again, that I proposed, it seems like a short time ago, but it actually was in 2002. And this concept of a magnetic racetrack, I still think is actually, it's even more interesting today than when I proposed it. When I proposed it, the fundamental principle that it requires, which is the movement of digital data in the form of the boundaries between the magnetic regions, we move them around the racetrack, as you can see in this cartoon, by current pulses that are passed into the racetrack, which is essentially a magnetic ribbon. And in this cartoon, you see the proposal I made was we could have a three-dimensional device in which these racetracks stand vertically. And then we would use conventional technologies to provide the circuits to access and write information into this racetrack. So each racetrack could store, let's say, 100 domain walls. And yet, within the racetrack, we would have one device for reading. It would be a magnetic tunnel junction device, and one device for writing information into the racetrack. And this means that this storage capacity of such a solid-state memory would be at least 100 times higher than any existing memory technology. And today, this is even more exciting because when I first proposed this concept, it hadn't even been demonstrated that current could move these domain walls in the way that this cartoon shows. All the domain walls have to be moved at the same speed if this is to be a useful technology. And of course, it's a non-volatile technology again. So this racetrack, if we are successful, could replace a magnetic hard disk drive. It would have capacities that probably would be superior. It would be 1 million times faster to access the first bit of information, would use much less energy, and would be totally reliable because there are no moving parts. The information we're moving is only the spin of the electron. We're actually not moving any atoms. There's no mechanical motion. It's a purely spintronic device. And I'd like to say a few words about this in the next few foils. First, let me show you how the simplest concept for moving a magnetic domain wall works. And this is based on a principle that a famous scientist from my alma mater, Cambridge, Neville Mott, first proposed nearly 100 years ago, soon after the spin concept was developed. And the concept is shown in the top. If you take a current from a battery, it will consist of equal numbers of spin up and spin down electrons. But these electrons are scattered at different rates within a magnetic material which is magnetized in one direction. So the electrons with their spins parallel to that magnetic moment will be less scattered than those that are antiparallel. And this means that within a very short length scale, the current within that magnetic material is carried by electrons of one spin polarization. And that, as I mentioned before, means the current carries spin angular momentum. So in the bottom part, you can see a cartoon. This is actually taken from Sadimichi Maekawa, who's a theorist in Japan. And the concept here is that this orange racetrack, on the left side, the magnetic moment is pointing to your right, and on the right side, to your left. In between, we have this domain wall, a transition. And as the conduction electrons in the current cross this wall with their spin polarized in one direction on the left, it will rotate to the opposite direction and deliver a quantum of spin angular momentum into the domain wall. And this causes a magnetic moment in the domain wall to rotate because angular momentum is a conserved quantity. So with enough current, we can cause all the moments in the domain wall to rotate, and the domain wall will move. And this is something that is very interesting, and what it means is that all the domain walls will move in the same direction in such a principle. This is called a spin transfer torque. We transfer spin angular momentum from the current into the domain wall. And that's something that we first demonstrated in 2008. So it took 8 years after my proposal before we demonstrated the fundamental principle works. Now, in the next 10 years or so, we actually discovered entirely new ways for manipulating, moving a series of magnetic domain walls, for moving the magnetic information using alternative methods to create spin currents. And this means that we use a very interesting phenomenon. It's called a spin Hall effect. If you pass current in a non-magnetic material, if it has strong spin orbit coupling, that charge current will be converted into a spin current, a pure spin current that flows perpendicular to the charge current and with the polarization perpendicular to both those directions. And so this means if we have a non-magnetic metal like platinum or tungsten, and we put on top this magnetic racetrack, we can create a spin current within this tungsten or platinum layer, and the spin current will diffuse into the magnetic material and provide spin angular momentum very effectively for moving these domain walls. And again, the domain walls will move in the same direction, all in the same direction, but only if these domain walls have a chirality that is the same for each domain wall. And it turns out this is something that we first realized and demonstrated. It turns out the same metal layers, like platinum, that generate these large spin currents through the spin Hall effect will also set the chirality of these domain walls in the racetrack memory through an interfacial effect that I want to briefly discuss. So I can't really tell you about all the physics of manipulating magnetic domain walls, but we and others over the last 10 years have developed new physics and new materials that enable us to move these domain walls at speeds of up to 1 kilometer per second. And this is approximately 10 times higher than is possible using the spin transfer torque mechanism that I mentioned in my previous foil. So in that 10 years, we've discovered entirely new unanticipated physics that enables us to move these domain walls much more efficiently, 10 times more efficiently than was possible just 5 years ago. And so I think this makes racetrack even more exciting. And then here, how do we do these experiments? In the laboratory, we make micron-wide racetracks. These are horizontal racetracks. We introduce, let's say in this case, 20 domain walls, and we then insert pulses of current on the nanosecond-long pulses. And then we use a technique called magneto-optic Kerr microscopy. By shining light, which is polarized on a magnetic material, the polarization will slightly rotate depending upon whether the magnetic moment is pointing up or down. And in this way, we can detect these domain walls. And we can then explore how these walls respond to current pulses. And in this way, we can detect the efficiency of motion of these domain walls. So at the top, this is a very simple racetrack. If you look on the right-hand side, you'll see that it consists of atomically thin cobalt and nickel layers. The whole stack is just 1 nanometer thick. Each of these layers are just a few angstroms thick. We can make these by conventional sputtering techniques that are mass manufacturable, and you can see we could build a racetrack in which, in the top, the domain walls were moving under the presence of current at speeds of about 300 meters per second. Well, 5 years ago, we invented, and this is an invention based on my original work for the spin valve recording heads, we invented something called a synthetic anti-ferromagnetic racetrack, where we make 2 copies of the racetrack. We put 1 copy on top of the other, but the second copy is a mirror image of the first one. For example, this means in the bottom racetrack, if the magnetization points up, in the top racetrack, it will point down, and the net magnetization in the net racetrack goes to 0. This is super important because, as I mentioned before, transitions in magnetic material will give rise to dipole fields. And these dipole fields cause interactions between the domains in a racetrack and between neighboring racetracks. You have to eliminate these long-range dipole fields by essentially making a magnetic racetrack that has no net magnetization. This is crucial. And it turns out when we did this, we discovered that this synthetic anti-ferromagnetic racetrack could move these domain walls 5 times more efficiently than in a simpler racetrack. And this means that it's fantastic for applications. The most perfect racetrack actually has the most perfect motion of these domain walls under current pulses. So this was an amazing breakthrough, and this means that racetracks, not only can we manufacture them, but they actually can make the most useful racetracks are those in which the domain walls can be moved most efficiently. Over the last 3 years in my institute in Germany, we've actually shown we can shrink the width of these racetracks, these are micron wide, to racetracks which are just 50 nanometers wide, and essentially we see the same efficiency of motion of these domain walls with current. And so this, we believe, means that we're very close to taking these devices from the laboratory into the world of manufacturing. And in fact, we have support from Samsung to do this in my institute. So I, again, don't want to spend too much time on the science of the domain wall motion. I'd like to move to another topic, but I just want to point out that there are 5 important elements to making this magnetic racetrack work. And one of these is we need these atomically thin, I mentioned cobalt and nickel, each layer is just 3 to 5 angstroms thick, but the interfaces break symmetry and cause the magnetic moments to want to be perpendicular to these interfaces. This is key to racetrack. We need perpendicularly magnetized racetracks. And at the same time, I mentioned we use platinum underlayer to create, through the spin Hall effect, spin currents, which we use to generate spin angular momentum. So what's amazing is that this spin Hall effect was proposed theoretically, but just 10 years ago, it was thought that in conventional metals, it was a very tiny effect. So we and others have shown that it's a very large effect. And today, in some unpublished work, we have materials, simple metal, binary metal alloys, in which for every electron, every charged electron we pass through this binary alloy metal layer, we can create 1 spin polarized electron. It's super efficient, has an efficiency of conversion of charge to spin current 5 times higher than the best material known to date, which is platinum. And I want to briefly mention one of the other physical attributes that make this possible is something called a Dzyaloshinskii-Maria interaction. And I want to briefly explain what that is. It basically sets the chirality of the domain walls. In this cartoon, you can see the red region is magnetized up, and the blue region is magnetized down. In the domain wall, the magnetization rotates from up to down in some fashion. And it turns out it rotates from up to down in a plane perpendicular to the wall, and it rotates from up to down in a clockwise fashion, in a chiral fashion, set by an interaction of these cobalt nickel layers with the platinum at the interface. This interface gives rise to what is called a Dzyaloshinskii-Maria exchange interaction, which is a vector interaction. It has a direction associated with it. And this is the only reason why these domain walls all move in the same direction under current pulses, under these so-called spin orbit torques created from spin currents in these metal underlayers. And so I just wanted to point out, what does that mean? What does that mean? It means in a ferromagnet, magnetic moments, neighboring moments, want to be ferromagnetic or antiferromagnetic through an exchange interaction that Heisenberg originally proposed. And this is all conventional ferromagnets and antiferromagnets behave in this way. They're collinear, either pointing up or opposite to one another. But in some materials, in the bulk, or in our cases at an interface, this breaks the symmetry such that the moments, neighboring magnetic moments, no longer want to be parallel or antiparallel. They want to be perpendicular to one another in a chiral fashion, either clockwise or anticlockwise. And this is created at an interface between a magnetic layer and, let's say, a heavy metal layer like platinum. This gives rise to this interaction, causing the magnetic moments want to be perpendicular and sets the chirality of these domain walls. But at the same time, this same so-called vector exchange interaction that defines chirality can give rise to some very interesting spin textures, which were only discovered approximately a decade ago. And these are shown here in this cartoon. What does it mean? It means that a magnetic material, instead of having all the magnetic moments parallel to one another, will break up into a ground state in which it consists of these circular, an array of these tiny circular objects, skyrmions and antiskyrmions. And in the interior of this object, the magnetization is in the opposite direction to the outside. The reason why it does this is because the boundary is stabilized by a Dzerzhinsky-Maria exchange interaction, and it lowers the energy of the system. But it turns out that depending upon the crystal symmetry, the sign of this Dzerzhinsky-Maria interaction can change depending upon the direction in the material. In simple cubic materials, then we have what is called on the left-hand side a block skyrmion. The wall between the outside magnetized up and the inside pointing down is a block wall where the magnetization rotates from up to down in a plane parallel to the tangent of this circle. On the right-hand side, in a nail skyrmion, the magnetization rotates from up to down in a plane along the radius of this device. In both cases, the rotation would be clockwise or anti-clockwise, depending upon the sign of this Dzerzhinsky-Maria exchange interaction. But it turns out that there's an even more complicated object. It's called an antiskyrmion. And in an antiskyrmion, as you rotate around this circular boundary, the boundary would change alternately between a nail and a block-like wall, and the chirality will change too. And this happens in some very special materials that I want to briefly introduce. So you might say, well, how can we detect and measure these devices, these objects? And we can detect them using, for example, a transmission electron microscope. In our case, we take a single crystal of this material, we cut a thin sliver using focused ion beam milling, and the sliver has to be transparent to the electron beam in a transmission electron microscope. So in our case, we use energy of the beam is 300,000 volts. It can be transmitted through a thin sliver, approximately 100 nanometers thick. And when the electrons transverse this thin sliver, they will be manipulated by the magnetization in the plane, and they will be through Lorentz forces that cause the electrons to move to the left or to the right, depending upon the direction of the in-plane component of the magnetization. So we can actually calculate then, what do we expect to see if our material has a block skyrmion, or it has a nail skyrmion, or it has an anti-skyrmion. And so we use micromagnetic simulations to calculate these objects, and then we similarly calculate how the electron beam transversing through them will be deflected by the magnetization components in the plane. And this is what it would look like. In the left-hand side, you can see a block skyrmion. In the transmitted electron beam, there will be an increased intensity in the middle, and you see basically a white blob. And a nail skyrmion, it turns out, because the beam is deflected around the circumference of the object, you would see nothing at all. And in the anti-skyrmion, we predicted, or we calculated, we should expect to see this 4 clover-leaf-like intensity, where you see these white regions of increased intensity of electrons and the two black regions horizontally of decreased intensity. And this is what we observed in a material called a Heusler compound. The Heusler compounds are very famous because the first Heusler compound, which was a magnetic material, had no magnetic elements in the compound. But the Heusler compounds are a huge family of thousands of materials. They're comprised of 4 intersecting FCC lattices. And in some cases, the ones which are magnetic, if we incorporate manganese, then the structure is distorted. It becomes no longer cubic, it's tetragonal. And this leads to a tetragonal axis along which the magnetization will preferentially point. This is shown in this cartoon. For example, it could be a compound manganese 2 platinum tin. In this material, the structure consists of layers of manganese and tin and layers of manganese and platinum. All the manganese atoms in one plane are oriented with their moments parallel to one another, and in the next plane too, but the two planes have their moments anti-parallel to one another. This is a so-called ferrimagnet, and this is a very interesting set of family of materials in which we anticipated that they would show skyrmionic behavior, or rather anti-skyrmionic behavior, based on the underlying crystal symmetry. And this is what we were able to see. In this manganese 2 platinum tin compound, we saw for the first time an anti-skyrmion. So in the top left, perhaps you can see the Lorentz transmission electron micrograph, and you can see the 2 white blobs and the 2 black blobs, and that is a signature of an anti-skyrmion. So this is the first observation, and we were the first to show this. We published this in Nature 4 years ago. And the other Lorentz micrographs show you that typically you'd find arrays, hexagonal arrays of these objects. The anti-skyrmions themselves, the size of these are determined by the ratio of this Dzerzhinsky-Maria exchange, which in this case is generated through the platinum moments within the material, and the Heisenberg exchange. And so the size of these objects are of the order of 20 nanometers, or as it will show you, can be increased to microns in size. And that's what I'd like to briefly discuss next. But I also wanted to point out then that what this foil shows you is that we make, using focused ion beam milling, we cut from a crystal not a flat lamina, but we cut a lamina whose thickness changes from one end to the other. And in this way, we can explore the properties of these anti-skyrmions as a function of the thickness of the lamella in which we are observing them. If we apply a large enough magnetic field, then all the skyrmions will disappear and the magnetization will be parallel. And so in the top, if you look at B, for example, on the left-hand side, the Lorentz micrograph shows you what happens when the magnetic field is large enough that all these interesting spin textures are eliminated. As we reduce the magnetic field, we start to see, and I think you can see, these white blobs, which are the anti-skyrmions, as observed through this Lorentz transmission electron microscopy. And on the very right-hand side, you can see we see a different spin texture. It turns out that in zero magnetic field, the spin texture that is favored is neither parallel magnetization, it's not an array of these anti-skyrmions, it's rather a helical structure in which the magnetization rotates in one direction from an up to a down periodically with a certain period. Again, and in this case, these helical structures are oriented along 2 crystal directions within the Heusler compound that favors block type walls, because those walls have the lower energy than the nail type walls. So these helical structures are tied to the underlying crystal lattice. And what we discovered, I don't know if you can see this, here is a Lorentz micrograph, an image. Basically, as I said, we're imaging effectively the in-plane component of the magnetization. And you can see this is an image taken for a wedge structure whose thickness is thinner on the right-hand side than on the left-hand side. And you can see perhaps these alternating black and white regions which correspond to the in-plane magnetization rotating in this helical structure. We discovered that the length of this period of this oscillation changes as a function of increasing thickness of this lamella, increasing from 100 nanometers in a lamella 20 nanometers thick or 40 nanometers thick to 200 nanometers in a lamella which is 140 nanometers thick. And this is the first time this had been observed in any of these spin textures. It hadn't been observed for nail skyrmions, for example, in any of the many systems in which nail skyrmions had been observed. Today, this is still the only system in which these anti-skyrmions have been observed. Instead of using Lorentz microscopy, we could use another technique of magnetic force microscopy, where we use a magnetic tip is moved over the surface of this lamella, and we detect the outer plane component of magnetization as the current tunnels from the tip into the magnetic material. And you can see here very beautifully, you can see this periodic alternating structure as the magnetization rotates from out of plane to in plane along this lamella. And what we found then is that as we increase the thickness beyond thicknesses that are accessible in a transmission electron microscope, we observed that the period would continue to increase of the helix as we increase the thickness. And it turns out this reflects, we could show from calculations, the important role of long-range magnetic dipole fields in this system, which turns out to be much more important than in skyrmionic systems. And in fact, if we can actually make lamella microns thick, and we see a monotonic variation of this helical period for lamella increasing in thickness from 100 nanometers up to 4 microns. And the size is increasing up to more than 1 micron. We can actually now visualize them using conventional optical means. And here you see a lamella whose thickness is increased from the left-hand side to the right-hand side. I'm not sure you could read it, but it's increased from 0.4 to 4 microns in thickness from left to right. And you can see the image under the magnetic force microscope of these helical structures. We can change these orientations by magnetic fields. But also by magnetic fields, we can turn this is the same lamella, we can turn those helical structures into arrays of anti-skyrmions, which in the magnetic force microscope, where we detect the out-of-plane component of magnetization, simply look like these little dots. But I think you can see from left to right, the diameter of the dots is increasing as the thickness of the lamella increases. And the diameter of these anti-skyrmions matches 1:1 for the period of the helical structures that we observe in smaller magnetic fields. So this was very interesting that we could tune the size of these objects, and this is potentially very interesting for technological applications. And the reason why we're interested is that in a magnetic racetrack, we could potentially replace a chiral domain wall with one of these chiral spin objects, and this could have some potential advantages. Now, I wanted to mention that these are anti-skyrmions, and why these are interesting is because these anti-skyrmions are topologically protected. This means because of the nature of this spin texture, it's difficult to transform it into another texture. This is why we were surprised that in this same Heusler compound, we were the first to show that there's a second topological spin texture that exists. And we called it it's an elliptical block skyrmion. And I think you can see here that we're switching back to Lorentz microscopy, then the image of these objects is entirely different from the anti-skyrmion. Now we see simple helical textures, and these are block skyrmions whose direction, or the long axis of the helix, is oriented along the same directions as the period of this helical structure that we observe in smaller magnetic fields. And the reason for all of this is the role of dipole fields that stabilizes these block-like walls in these objects. So why is this interesting? Well, potentially, we could store information in a racetrack, not in the absence or presence of a spin texture, but we could store, let's say, zeros as an anti-skyrmion, and we could store ones as a elliptical block skyrmion. And this is what we can demonstrate by making out of these material racetracks, which are narrow in their width. But I just wanted to point out then that there's a competition in these objects between dipole fields that favor these block walls and therefore the elliptical block skyrmions, or if the system shows anti-skyrmions, it will cause distortions in their structure so that the anti-skyrmion, which I said has nail and block walls, the block wall components become larger, and then the anti-skyrmions look like these square objects that you see on the top right-hand side. So essentially, this is in a temperature range where the Dieleczinski-Maria interaction is dominant and the structure is perturbed by dipole-dipole interactions, whereas at lower temperatures, where the magnetization is bigger, dipole-dipole interactions are important. We see these elliptical block skyrmions, which are distorted by the Dieleczinski-Maria exchange interaction. So this is a very interesting system where we can probe the interactions and how they compete in this way. At the same time, then, we could make racetracks where in one racetrack we just see a single row of anti-skyrmions, or a single row of a combination of anti-skyrmions and block skyrmions, as shown here. So on the left-hand side, you can see our experiment where we can create a series of objects, some anti-skyrmions, some block skyrmions. They could correspond to zeros and ones. And on the right-hand side, you can see micromagnetic simulations of the same objects that we can use to confirm our experimental observations. So this is the idea. We could create a very interesting magnetic racetrack memory device with these two important topological chiral spin textures, as one as a 0 and one as a 1. Well, I think I'm running out of time. I wanted to say, look, we can even go beyond this. And recently, we've discovered something which we think is super interesting. We've discovered objects which are so-called fractional. So I mentioned that the anti-skyrmion and skyrmion are topological objects. That means they actually have a topological charge of 0 or 1. And we discovered a new object at the boundaries of these lamella, which have a fractional charge. And in collaboration with Daniel Loss, who's a theorist at the University of Basel, then they could confirm that these fractional objects should exist at the boundary of these arrays. And these hadn't been seen before, and we think this is a very interesting first discovery of fractional spin textures. It's not yet published. And then this is just some of the simulations from Daniel Loss and his collaborators who are showing how we can observe these fractional objects at the edges of our lamella, and they're stabilized. They exist only when the interior is filled with the arrays of anti-skyrmions or elliptical block skyrmions. So I think I've only got a couple of minutes left, so I wanted to just mention that there are other interesting systems which show different types of spin textures. And this is for example, just give you one example, platinum, manganese, gallium. It's a layered system. It was believed for 30 years that its structure was centrosymmetric and therefore should not sustain or support topological spin textures. Nevertheless, we discovered that we could see in this system, for the first time in a metallic system, nail skyrmions. And in principle, they shouldn't exist. However, I have a very, very good scientist in my group, Holger Meyerheim, who's an expert in X-ray diffraction. And he could show that actually the structure that people thought was centrosymmetric, it turns out there are distortions to the structure that can even be seen in the original work from 30 years ago. And that means that the structure actually has a broken symmetry. And this is the only reason why we can see these nail-like skyrmions at relatively high temperatures. And in this system also, this is a magnetic force microscopy image where we've created a lamella, again with thickness varying, thin on the left, thick on the right, and you can see these red objects, which are the magnetization of the system. They can increase in size, and we again found this very interesting size dependence of these objects on the thickness of the lamella in which they exist. And again, this is because of a competition between dipole-dipole interactions and exchange. And finally, I just wanted to mention, because I know there's a lot of interest here in 2D systems, 2D materials have become a very hot topic in the world of physics in the last few years. And one of the magnetic 2D materials is something called this iron 3 germanium tellurium 2. It's a layered system. Again, it should be centrosymmetric. Nevertheless, again, by very careful and X-ray diffraction, we found that in this structure, the occupancy of the ion sites is distinct. There's some vacancies. And these vacancies in the ion sites break the center of symmetry and can account for the observation that we made, again, of nail skyrmions in the system whose size scales with the thickness of the layer in which we are imaging them. So this is a very interesting observation, and I think there's been a lot of interest in the community of 2D materials as to why such a system, which is centrosymmetric, could display these chiral spin textures. Now we know why, in fact, the structure is not what people thought it was. This seems to be a common theme, that the structures of some of these material systems are much more interesting and complex than had been appreciated. So I want to summarize by then, having given you a short introduction to magnetic racetrack memory, mentioned that in these engineered synthetic anti-ferromagnetic racetracks, we can use current pulses to move a series of domain rules at speeds exceeding 1 kilometer per second. Well, that means, firstly, we could replace a magnetic disk drive with these magnetic racetrack memory devices to provide a solid-state, highly reliable, highly low energy and high performance memory if we use 100 domain rules per racetrack. On the other hand, we could build a very short racetrack with a single domain rule, move it backwards to the left or to the right, and that would only take 100 picoseconds, and we've shown this experimentally in real devices which are 50 nanometers wide. This would enable us to build a 1-bit memory that could replace static random access memory. Static random access memory is the fastest memory used today, and it's at the heart of the performance of computing systems. The computing cores have coupled to static random access memory, but this memory takes a huge amount of space, limiting the performance of computing systems. With racetrack, a single domain wall racetrack, we could build a super high performance, low energy consuming, non-volatile memory that would be, and have more memory. This would make the performance of computing systems much more powerful. And I think this type of racetrack memory, with the developments that we've made over the last 10 years, will make it into the marketplace in the next few years. And the rest of my talk, I just briefly mentioned some of our own work on spin textures, chiral spin textures. And we've observed for the first time anti-skyrmions, elliptical block skyrmions, and nail skyrmions in metallic systems. And a common feature of many of these systems is how the size of these objects can be systematically varied simply by controlling the thickness of the material. But it means more than that. We can control it in other ways more deliberately by engineering Dieliczinski-Maria on the one hand and dipole-dipole interactions on the other hand. So I'd like to thank you very much for the opportunity to tell you something about our work in spintronics over the last few years. Thank you very much for your attention.
Thank you, Professor Parkin, for sharing your interesting work with us. May I request you to remain on stage? And I would like to invite Professor Sam-C Chian, Director, Institute of Advanced Studies, on stage to be the moderator for the question and answer session.
Okay, the moment we are all waiting for, a very inspiring talk, very exciting research. So we have a number of good questions, a lot of questions from the audience. Okay, so let me start with the first one. Recently, there are a lot of efforts from semiconductor fields to design 3D NAND vertically to enhance the performance of memory cells. With your strong background about spintronics and physics, do you think what could be the next move to improve the memory cells in the future?
Okay, that's a good question. So 3D NAND is a fantastic technology where instead of shrinking a flash memory cell, which is basically a capacitor, to smaller dimensions, it's not possible because there aren't enough electrons. Instead, you keep the size and you build flash memory cells one on top of each other. And this is a technology invented by Samsung. And they invented very clever ways of accessing 100, I think they've exceeded 132 more layers of these capacitance cells. So we believe, in fact, working with Samsung, we believe that racetrack memory could replace NAND, because NAND has a problem, it's very slow. And it's not possible to scale it any further because the number of electrons per capacitor is so tiny, it's just not possible. This is the reason why they have to maintain a certain size and build more layers. But it's not possible to build many more layers. It's just not feasible. So you need a totally new technology, not based on the electron's charge. So the racetrack is, if we build horizontal racetracks, we could, just like VNAND, we could build one on top of another and access all of these racetracks. We could build a superior technology because instead of hundreds of layers, we would only need a few layers of this racetrack to achieve the same capacity but with much greater performance.
Okay, thank you. I hope that answers the question. Okay, another question. Currently, different types of storage methods or devices are in extensive R&D. Example, 3D NAND, heat-assisted magnetic recording, spintronics, etc. Which one will be the most impactful for the technological paradigm shift, in your opinion?
So I think, heat-assisted, I think recording you mentioned, that's one approach. The problem with magnetic disk drives is that you cannot shrink the size of these magnetic regions any further because there isn't enough magnetic anisotropy, enough magnetic energy to maintain the direction of these units against thermal fluctuations. So to avoid that, you use, and the reason is that the recording writing heads cannot create enough magnetic field to write into layers which have a strong enough anisotropy to overcome temperature. So what you have to do, you have to write very anisotropic materials which cannot be written unless you heat them up. And there are two approaches to heating them, either with light or with RF excitations. And Western Digital and Seagate have two different approaches. However, that's technologically very difficult and hasn't yet, I believe, found its way into the marketplace. And there are other reasons why it's very difficult then, as you shrink the dimensions of these magnetic units, for the writing and reading head to find them, to follow these tracks. This is also extremely difficult. So I think we need to go beyond this 50-year-old technology and do something else, such as with the magnetic racetrack, which I think is the most interesting approach today.
Thank you, Stuart. Okay, another question for you. How prevalent are the Joule heating effects in racetrack memory? What current densities occur in these systems?
So the current densities that we are typically using are of the order of 10 to the 8 amps per square centimeter. So what does that mean? That means we're limited indeed by heating. If we increase the current density beyond these numbers, then you will get significant heating. It's a highly nonlinear effect. But at these kinds of densities, there is no significant heating of the racetracks. So Joule heating is not important. However, the concept of using heating, just like magnetic recording, heat-assisted magnetic recording, is a very interesting one. And one could potentially use thermal effects to aid the motion of the domain walls in clever ways.
Okay, thanks, Stuart. Hope that answers the question. Okay, here's one. What do you think is unique about the composition that allows antiskyrmions to exist within the system?
Oh, so that's very simple. It simply depends on the underlying point group symmetry. And the symmetries determine the symmetry of this Dzyulinski-Maria exchange vector. It has to be coupled to the underlying crystal symmetry. So we can already predict which types of systems would show antiskyrmions or other objects.
Okay, so here's another question. Skyrmions appear like droplets, even exhibiting droplets merging-like behavior. Is there any parameter in skyrmions similar to surface tension in droplets?
Surface tension. Well, I guess it is in a way. I mean, this domain wall has an energy, and it turns out it has a reduced energy. This is why we form these objects that in a skyrmion or anti-skyrmion, the reason for their formation is that you can lower the energy by this Delizinski-Maria exchange energy by having the moments being perpendicular to one another. So in some sense, there is some kind of analogy to surface tension.
See. Okay, can one detect skyrmions and anti-skyrmions using an electrical method? Are they pinned or can they be manipulated?
Yes, you can manipulate. Of course, you can create a skyrmion or an anti-skyrmion by injecting angular momentum to reverse the local magnetization in a small area, and then you would, in principle, create a skyrmion or anti-skyrmion. So it's in principle possible.
Okay.
Or you could use optics. So if you use appropriate photons, they can also deliver angular momentum, and you could use concentrated light to create spin textures.
Okay, how fast could a racetrack architecture based on skyrmions and anti-skyrmions could be?
So it turns out currently skyrmions and anti-skyrmions cannot be effectively moved because basically the chiral domain walls that I mentioned earlier on, essentially a skyrmion is a chiral domain wall. But it turns out the most effective means of manipulating a chiral domain wall is in a synthetic antiferromagnet. The reason is that the two mirror copies of the racetrack are coupled antiferromagnetically through an exchange field. And the strength of this exchange field gives rise to an additional torque that can manipulate the domain walls. It turns out because that exchange field, the coupling strength, antiferromagnetic coupling strength, is several times higher than the effective field associated with the Delizinski-Maria exchange interaction, we can manipulate domain walls in a synthetic antiferromagnetic racetrack much more efficiently than in a single magnetic material. So to date, skyrmions, anti-skyrmions exist in a magnetic material, and they cannot benefit from the giant exchange torque that we discovered in these synthetic antiferromagnets. So it's much less efficient to move skyrmions or anti-skyrmions with current than it is to move a chiral domain wall.
Okay, I hope that answers the question. Okay, how does the mixed chirality of an anti-skyrmion influence its mobility under a spin orbit top? Can one expect any anisotropy in its mobility?
Well, it's a very good question, and it turns out that because I mentioned the chirality changes from one part of the anti-skyrmion to the next part, it means that current, which is driving this device, will, depending upon the direction of the current, whether you pass the current through the nail wall component or whether you pass it along the block wall component, then the skyrmions will respond differently. And in fact, in one case they move to the right, and in the other case they move to the right through a so-called skyrmion Hall effect. So regular cubic skyrmions, when you pass current, because it's cubic, they will move either to the left or to the right, depending upon their chirality. This makes it difficult to use skyrmions technologically, because along a racetrack, they don't move in a straight line, they move to the edges where they're likely to be disturbed. However, in an anti-skyrmion, because if you pass current in one direction, it'll go to the left, and 45 degrees or 90 degrees will go to the right. At an intermediate angle, it goes in a straight line. So this is actually, there's no skyrmion Hall effect. We can calculate this for an anti-skyrmion, a spin orbit torque. If you pass the spin orbit torque along the correct direction, then the anti-skyrmions will move in straight lines. This makes them very interesting. And as I mentioned at the beginning, we actually see these anti-skyrmions in a Heusler compound, which is not a pure ferromagnet, it's a ferrimagnet, where you have one magnetic layer of manganese pointing up and a second one pointing down. In a regular Heusler compound, the moments in these two manganese layers, manganese platinum, manganese tin, have different values. However, we can chemically tune the system so these moments would have the same value. If we can do that, likely is that we would then see a similar effect as in our synthetic antiferromagnet, that we would see an additional torque in our ability to move under spin orbit torques, these objects. So if we can do that, plus, in those cases anyway, this Skyrmion Hall effect would go to zero. So this is very interesting. So I think by tuning chemically the Heusler compound, we should be able to find a material in which these anti-skyrmions would move at high speed and in the direction of the current, making them the most potentially useful object for racetracks.
Okay, thank you. I hope that answers the question. Actually, I have a question. I noticed your phase diagram for the elliptical skyrmions, the coexistence of the elliptical skyrmions. They coexist with the anti-skyrmions at around 270 Kelvin. So I was just wondering, the stoichiometry of the system, tuning the stoichiometry system, would that help to increase the operating temperature? Does it matter with the,
it would.
composition?
So if we could tune the magnetization to go to zero, then the dipole-dipole effects should also go to zero. And then it would be easier to tune one or the other. So you're right, by tuning, we could tune the stability of these objects.
Because it's a competition, if I understand that there are two effects that are competing.
That's exactly right. One of these objects, the block skyrmion, because the walls are entirely block-like, stabilized by dipole-dipole interactions. So if you eliminate those, you'll stabilize the anti-skyrmion, or vice versa. So it's possible by tuning chemically, you can tune the magnetization, and you can tune the contributions of the Delizinski, the vector exchange, and the dipole-dipole interactions.
Okay, thank you. Okay, here's a question from our young PhD students. What would be your advice for first-year PhD student who has too many interests that cannot focus well? Even he knows it could be better work on topics one by one.
Oh, that's a very good question. I think it's, of course, if you are scattered amongst too many projects, then it's unlikely you'll have much success in any of them. And I think some of these topics are incredibly difficult. And I think focusing on one and learning about that one topic perhaps would be more rewarding.
Okay, I hope that answers your question. Okay, here's another one. What pragmatic method do you propose to read anti-skyrmions in a working racetrack memory device? It cannot be done via Lorentz TM.
Yeah, that's a very good point, and it's very difficult to read skyrmions and anti-skyrmions, whereas chiral domain walls can be read much more effectively. So I think this is a major problem with skyrmionics.
Okay. So in-memory computing or processing in-memory takes the resistance of spin transfer torque, magnetic RAM, and domain wall memory to do computation inside the memory. They can conduct Boolean operations like AND, XOR, and arithmetic addition and subtraction operations. What do you think about this field?
So in-memory computing is a very interesting field in which tries to overcome this von Neumann dilemma of moving data from memory into computing systems by having one system that can compute and can store information. This is the concept. So it's a very interesting concept, and perhaps in spintronics there are ways in which we could carry out computing in elements which we have domain walls. It's certainly possible to imagine all sorts of ways in which you can carry out computing with the chiral domain walls or even with skyrmions, which would allow for in-memory computing.
So in fact, I think recently Samsung just reported, I think just published in Nature just a couple of days ago, the first demonstration of in-memory computing.
Oh, using which technique?
Yeah, MRAM.
Oh, okay, very good.
Yeah. Okay, here's another one. What is the physical mechanism behind the thickness dependence of chiral spin structures? Second question, how does the elliptical skyrmions stabilize?
So the second question is the elliptical skyrmion is stabilized by dipole-dipole interactions, which favor block wall over nair wall. And that's a very fundamental principle. And the first question I couldn't hear what you said.
The first question is, what is the physical mechanism behind the thickness dependence of the chiral space?
Thickness depends. Oh, that's simply because as you increase the thickness, the role of dipole contributions changes in ways that is very interesting. So, for example, if we take this Heusler compound and make a layer that is 1 unit cell thick, the skyrmions will be 10 times larger than if we make it slightly thicker because of the role of dipole-dipole interactions. And the role of dipole-dipole interactions, it causes a shrinkage of the size of these anti-skyrmions. And this is it's a competition between these long-range dipole-dipole interactions and the fundamental exchange interactions themselves.
Okay. So we have last 2 questions because time is coming up. So what is your internal inspiration or attitude to create and pursue your research career path as a key takeaway for young scientists and engineers?
I don't know, that's a difficult question. I just find so many things very interesting. And I also find it very, very interesting if you can think of a way of using a phenomena to have impact technologically. So for me, I find this intersection of fundamental science, and in particular, for me, what I find very inspiring is the notion of building new materials, one atomic layer at a time. And then typically the interfaces have properties that are distinct from the individual material components. And moreover, it's super interesting because it's very, very difficult to calculate the properties of interfaces. So today, for example, I have a collaboration with André Benevig, who's one of the world's best solid-state theorists. He's at Princeton. And he can calculate all 500,000 materials in the inorganic chemical database and tell you something about their electronic properties, whether they can have surface states, and so on. But if you ask him, well, what about an interface between 500,000 materials and any 500,000, it's impossible today. Not only the computing resources are beyond what is possible today, but one simply doesn't know how material A will stack on material B. And we know, let's say, from twistronics and Murari systems, that changing the angle by even of 1 degree can completely change the properties through flat band effects. So I think what is really interesting is, in my mind, is interfaces. And my own actually current interest is to create new types of superconductors. Superconducting materials can carry current without any joule heating, no dissipation. But currents, in principle, can carry angular momentum if you have a triplet superconductivity. And we've recently demonstrated the long-range development of triplet supercurrents by combining very interesting exotic materials with conventional superconductors. And my current goal is to demonstrate that these triplet supercurrents, we can actually cause the spins of the Kuiper pairs to be aligned parallel in a state 1 and carry spin angular momentum and use this to manipulate magnetization. And I think we can only do this at interfaces. So you have entirely new possibilities of the science at interfaces and technological impact of those interfaces. And that's what my current interest is.
Thank you. Just the last question. How would you envisage the applications for fractional anti-skyrmions and fractional elliptical block skyrmions?
Oh, that's very difficult. So we've only just discovered them. And currently, they only exist at the boundaries. We believe in this. It turns out there's something called a bulk boundary correspondence. They only exist at the boundaries because of what's inside the material. It's not clear how you could use these objects, but that remains to be seen.
Okay, thank you. Okay, ladies and gentlemen, time flies very quickly when we are enjoying ourselves with this very intense intellectual discourse. I enjoyed this very much. I hope you do enjoy this as much as I do. So the Institute of Advanced Studies is committed to promoting and bringing science at the highest level. So Prof. Parkin's achievements are a great inspiration for all of us here to reach to even greater heights. Now, this public lecture, such public lectures have been quite a rarity since the outbreak of the pandemic. And this public lecture would not have been possible without the strong support from NTU, from NRF, and also from the Lee Foundation. Now, I would like to thank my fellow IAS colleagues, Nripan, Chris, Narissa, and even Hui Ling, okay, as well as the CITS staff, as the events office staff, okay, who have worked very hard to put all these things together on a very short notice. And most importantly, I would like to express my sincere, deepest gratitude of Professor Parkin, okay, for his time to share his thoughts and give us such a very inspiring lecture. So let's put our hands together and give him a show of thanks to him.
Thank you very much.
Thank you, Professor Parkin and Professor Sam. May I request Professor Parkin and Professor Sam to remain on stage. I would like to now invite Professor Subra Suresh and Professor Simon Redfern back on stage to facilitate the presentation of Memento to Professor Parkin. This brings us to the end of the public lecture. I would like to thank everyone for your kind presence and those with us online. May I now invite our guests to remain seated while our speakers and senior management take their leave first. Lastly, we request all attendees to fill in the feedback form by scanning the QR code on the screen. Also, please indicate in the form if you need the endorsement for your attendance. Thank you once again for taking the time to join us today. Have a lovely evening ahead.